Hi, everybody. My name is Kyle Luna. I'm a fourth year student, and I'm going to be talking about magnetic resonance imaging, or MRI physics, and its interaction with pacemakers. So I don't know about you, but I was really excited to talk about this because when thinking about what to do this presentation on, I was thinking in the healthcare system, we have these huge cylindrical magnets, and I was thinking, like, what happens if somebody has an electronic device in their own body? It sounds like there can be some severe complications with that. So I'm going to go ahead and have a brief introduction, go over the physics of an MRI, introduce a cardiac implantable electronic device, or a pacemaker in this case, and some concerns and preventing complications, and then I'll conclude. So MRIs take advantage of the fact that our body is primarily made up of water. A strong magnetic field and radio wave pulse alter the orientation of the protons of the hydrogen nuclei in the body. I'll go over a little bit about this in the next slide. But essentially, when the radio wave pulse is emitted, it returns the magnetic vector to its resting state, causing a signal to be produced through a frequency. So MRI physics have raised concerns over its effects on cardiac implantable electronic devices such as pacemakers, and we're going to go over that right now. So I'm going to go ahead and have like a brief I'm gonna take you guys back to the first couple of weeks of class. So as you know, the hydrogen atom is a topic that we use a lot in this course. So I want you guys to imagine in your body you have the nuclei of hydrogen atoms randomly oriented and a net magnetization of 0. So you can imagine it, the magnetic field can look something like this in a 3D plane. So when you have a strong magnetic field, it brings them up to the top and points at it, basically. So when you introduce that and then introduce an RF pulse, it basically turns the magnetic field perpendicularly. And essentially, when that happens, when the pulse is emitted, it wants to go back to its initial state. So that basically not only emits energy, but it also takes in the energy. So the energy that it emits is in the form of a frequency. And in this case, it produces the rotational slash Larmor frequency. So this is pretty much what I was talking about here. The spins will acquire energy from the RF pulse. However, the spins will gradually return to the original lower energy states, like I mentioned. That's what we call T1, or spin lattice rotation relaxation. And T2 relaxation basically refers to the decay in time of the axial spin. Basically, you can think of it as you have all of them starting in the same phase, and then you basically measure the time it takes for all of them to be in different phases. So that's how you can think of the T2 relaxation. So yeah, MRIs basically exploit these relaxations and produce an image out of them. So you can think of it as it exploiting the fact that all the hydrogens are in unison, but they have different phases. So if you think of a grid of all the hydrogen atoms, and each one has a spin, and just each one is in different phases, basically the MRI takes that grid and it has a gradient coil that changes the phase of the rotating hydrogens to create stripe patterns by controlling how long the X and Y gradients are turned on. And they measure the phases in all different frequencies and orientations to produce an image. So here's pretty much what I was talking about. This is the RF transmitter and receiver, and these are pretty much just all the magnetic foils, and that's the image that it produces. So what about a pacemaker? So these devices send electrical pulses to the heart to prevent arrhythmia. That's basically when the heart beats too fast or too slow or is irregular. So some common features of a pacemaker is the reed switch and a power on reset, and you'll see why that's important. Basically, the reed switch acts as, they called it magnet mode, so it's like a fail-safe. It basically turns the pacing to an asynchronous pace, which is basically like a pre-programmed set amount or set pace of the heart beating. And the power on reset is basically a switch that basically factory resets it. The purpose of that is whenever the battery might be depleting or there's some sort of circuit failure within the device itself. So this may have adverse effects when under the conditions of an MRI. So I'm just going to jump through the biggest concerns. The first one is movement. So like I mentioned earlier, you can think of an electronic device and a huge magnet that has 10.5 Tesla. You can imagine that some sort of movement is going to go on here. So researchers have found that there are ferromagnetic components present in the battery and the reed switches. However, it is not a concern. Some studies have shown that the movement force was so low that it only experienced forces that are equivalent to the gravity, like what happens in basic gravity with the pacemaker. Heat emission, this is another one. The radio frequency pulse that I mentioned earlier can basically cause heat deposition in the tips of the leads of the pacemaker, and it could potentially damage the myocardial tissue. However, studies have shown that the severity of the heating varies on very different factors. And most in vivo studies show negligible effects on troponin levels or clinical outcomes. However, the issues start to arise when you start looking at the conduction of the leads. The MRI can induce electric currents in the leads, altering electrograms and causing dangerous arrhythmias. So as I mentioned, the reed switch, I know this image is very small, but essentially the reed switch, when it is closed, it provides sensing of the heartbeat so that it can determine what paces to make it at. So the MRI can basically alter the fact that the reed switch could be closed, could be opened, but it could close it automatically, setting it to the pre-programmed asynchronous pacing. This is while the patient is under the MRI, which is really bad. So it can disrupt the device function and essentially inhibiting the detection and treatment of the arrhythmias. And lastly, the power on reset is a safety feature that restores it to the factory default settings. They did talk about how this does happen a lot, but the paper that I was reading basically said that it's easy to pre-program afterwards, so it's not a huge deal, but I found that it is a concern if that is happening. So some ways that clinics and researchers are dealing with these issues is they create these diagrams or flowcharts, and it basically goes through the the criteria for determining if we should basically go through with an MRI or not, or just be cautious and see that the effects that it's having. So yeah, as you can see, it can range from pretty simple to pretty detailed and complex. Also, okay, 1 minute. All right, okay. All right, so there are MRI conditional devices that have been developed that basically mean that they're safe to be in MRI. And several studies have been made to record adverse events when performing an MRI on non-MRI conditional devices. And the results showed that no long-term clinically significant adverse effects were reported. However, that's not to say that everything was perfect. There were multiple reprogramming issues and read switches closing. So future directions, leadless pacemakers that will reduce the heating element that I mentioned and inducing the current. And research into pacing methods that do not rely on conductive material are also in consideration. So in conclusion, I basically went over the physics of the MRI briefly and the potential risks and the risks that may not be as serious. And some guidelines have been created by clinics and researchers, as well as briefly touched on the advanced devices and MRI technology that should basically eliminate the need for such guidelines, making MRI conditional pacemakers in patients more practical. And any questions?